The purpose of this video is to introduce the fundamental concepts associated with periodic signals. You may ask yourself, why do I care about periodic signals? Well, it turns out that whether or not a signal is periodic determines fundamentally how you treat it when you're doing Fourier analysis, in the sense that periodic signals have Fourier series expressions and non-periodic signals have Fourier transforms. So understanding whether or not a signal is periodic is essential for frequency domain analysis. So the definition of a periodic signal mathematically is that some signal x at a particular point in time t is equal to the same signal at a different point in time t plus cap t. So the idea is a periodic signal looks the same if I shift it by a factor of cap t. Cap t is called the period of the signal. As an example, suppose I have some nice sinusoidal looking signal like this, and it goes off in the same manner out to infinity and out to negative infinity. And we'll get rid of this. I don't know what happened there, but it's so unsightly. Okay, so the idea that this signal is periodic means that if I look at some particular point in time and see what the value of the signal is at that point in time, if I go one period along the time axis and look at the signal, so one period of this signal appears to me to be about here, this value and this value are the same. Okay, that's a periodic signal, and the period here is t. So just to reinforce the idea and add another ugly color, if I look at a different point in time, then my signal has that value. If I go one period farther, it has the same value. So again, the idea here is a periodic signal looks the same when you shift it by its period. Now, so I guess we'll point out that this is also t. Now, it turns out that we're usually interested in what's called the fundamental period. So I'll add a 0 here because this is actually the fundamental period. Fundamental period. And the idea is the fundamental period is the smallest distance you can shift the signal and have it look the same. Now, you'll notice that it's possible with this signal, if I look at this point and go out past one period to two periods, that the value over here is the same as the value over here, even though the distance from here to here is 2t0. So if a signal has a fundamental period of t0, it's also periodic whenever you have t equal to some integer k times t0. So a signal has a fundamental period t0, and then it's going to be periodic at 2 times t0, 3 times t0, and so on. Okay, so that's the fundamental idea behind periodicity. Some important things that we also think about when we look at periodicity. One is the fundamental frequency of the signal. This is 1 over the fundamental period. And the idea is that frequencies are measured in cycles per second. So basically the idea here is that if it takes me, say, if t0 is 2 seconds, then I have, so if I have the case just as an example, t0 is 2, then f0 is going to be 0.5. So that means my fundamental frequency is 0.5 cycles per second. It takes me 2 seconds to go through one single cycle. Quite often, you'll also see the quantity omega 0, which is 2 pi times f0, which then makes it equal to 2 pi over t0. Okay, and the idea here is that this is often called a frequency as well, but this is typically a radial frequency. Because this is defined in terms of radians per second. The place where you'll see this most often is typically when you're dealing with sinusoids, cosines and sines, because I can write a cosine of omega 0 t. This cosine has a period of t0. So that's why you oftentimes see this omega 0 used, is because it represents a radial frequency. The cosine of omega 0 t has a fundamental period of t0. So that's the introduction to periodic signals. Again, they're important. It's important to be able to tell whether a signal is periodic or not when you're doing Fourier analysis.